All right, guys. We're going to start our look into horizontal motion here. I'm going to try to make this video quick for you. Certainly, hopefully, nothing to do after class today. So let's just jump right into it. Okay. So we've spent lots of time, obviously, looking at applications of the derivative. We've seen a lot about related rates, optimizations, and maxes and mins. Another application of the derivative, really the last application of the derivative we're going to look at, is something called horizontal motion. And if you've taken physics, certain level of physics, you may have seen this, you may not have. I'm going to assume no knowledge from anybody on this. So if it's a repeat for you, great. If it's new, you're going to be, you should be fine. So it says, suppose I have a particle on the x-axis as per below. So what I'm actually going to do first is draw in some positions here. So imagine I have a particle that's on the x-axis, and I'm just putting in some random numbers here. Okay, you could put any numbers you want on the x-axis, but let's imagine I have a particle, okay, that's starting here at position 1. So what I have here on the x-axis is the particle's position that we'll denote with the letter S. Okay, S represents the position of the particle. A particle is somewhere on this horizontal axis. And over time, again, this is particle motion. Imagine this particle, okay, it's really moving on the x-axis, but just to make it clear for you, imagine a particle moving to the right to position 8, and then the particle moves back somewhere this way, and then the particle moves back on the x-axis, and ends up at position 10. Again, this is all taking place on the x-axis. It's not floating above it, but it's hard to represent the back and forth just on the x-axis. So imagine you have a particle that is kind of moving in that direction. It's shifting right, then it's shifting left, then it's shifting back right. Okay, that's what we're talking about when we talk about horizontal motion. It's not moving vertically, it's not moving diagonally, it's only moving in one direction. Okay, horizontally, and we can represent that via the axis there. Okay, but let's take this a little bit step further. So let's say I represent this particle's horizontal motion, okay, with this function s of t, where t again is time. So over time, time will be my input or on my x-axis, and this will be on my y-axis. It's horizontal position. Okay, so we ended up at 10. I'm just using what we did before. We went to 8. We started at 1. So if I'm representing this kind of using an x and y grid, where on the x-axis we have time, on the y-axis we have its horizontal position. Okay, let me go with blue here. My particle is starting here. Again, I'm kind of trying to replicate what I did above, that horizontal motion on the x-axis, using time on the x-axis and my horizontal position, okay, on the y-axis. So what happened? Really, over time, my particle, as time went on, my particle changed position. It went up to 8. Then, right, my particle went back down. And then, again, as time went along, okay, I finished at position 10. So that's another way to look at the horizontal motion of a particle. Okay? So my question for you then is, what does the derivative of s of t tell us? The derivative, again, would be your tangent line, right? So if I were to maybe just draw a tangent line there, okay? So there's my, an example tangent line. Now, tangent line would be represented by, okay, again, that's a slope, right, at a given point. If we think about slope, that would be your change in position or change in s over your change in time. Hopefully you agree with that, right? When we think about the slope of a line, if time is on the x-axis and y and horizontal position is on the y-axis, a slope would be the change in s, or the change in horizontal position, over change in time. Well, if you think about that, the change in position over change in time, that is just another way to represent velocity. Velocity is how far you've gone in a given amount of time. If you think about a car, right? And you're going 60 miles per hour, it represents how far you've gone, miles, over hours, how long it's taking you to do that. So if I'm representing my tangent line with a change in position or some change in time, that's going to be represented via velocity. Okay, velocity. So the derivative of a position function is going to be the velocity. Okay, so when we think about that, that's a really important thing. One thing to note with velocity, okay, is that sign matters. What I mean by that is that, for example, if you have a velocity of 3 miles per hour, okay, again, we're only thinking about horizontal motion of a particle, so don't try to confuse this with a car. When we think about horizontal motion, a positive velocity, okay, would mean a shift or a motion. I shouldn't say motion or shift. I should say motion right. And negative 3 miles per hour would represent a motion left on the horizontal axis. Again, you want to be, if we go back up here, right, you think about the horizontal motion of a particle, it matters whether the particle is shifting left or right, or whether the particle is shifting left. You want to denote, okay, not only is where the particle is moving, but how fast. So if the particle is moving right, we would represent that with a positive velocity. If it's moving left, we would represent it with a negative velocity. Again, you're changing position of the particle. We would want to be able to differentiate that. So velocity does have a sign does matter with velocity. Okay, positive means motion right, negative means motion left. So the question I have here at the bottom is, what does the derivative of s prime tell us? Okay, again, we know s prime to be velocity. We've kind of just discussed that, right? S prime is velocity. What would s double prime tell us? Well, s double prime, or the second derivative of s, it gives us the rate of change of velocity. Think about your car. When we talk about how fast your speed on your car is changing, what is that? It's also called the acceleration. So we would call it the rate of change of velocity, okay, the acceleration. Okay, so if we think about the hierarchy, s of t, s is usually used to represent position, not always, but s of t is usually represents the position of your particle. Okay, v of t, okay, is s prime of t. Usually we write v of t. We don't write s prime. We write v of t. But s prime of t is your velocity. And then instead of writing s double prime of t, we usually write a of t. But just note that a of t is the same thing as s double prime, and that's represented via your acceleration. Okay, so when I write s of t, I mean position. If I write v of t, I mean the derivative of your position function or velocity. And a of t is represented, can be represented using s double prime, which is acceleration. Again, typically this is what you're going to write. You're going to write s, v, and a. And you should just kind of know how those all relate to each other, okay? All right, so let's look at maybe one or two problems, and I'll let you go. Example 1, a particle is moving or moves along the x-axis so that its position at any time is given by s of t equals the inverse tan of t for t is greater than or equal to 0. You can't have t less than or equal to 0 if t represents time. You can't have negative time. So it says prove the particle is always moving to the right. If it's always moving to the right, thinking back to what we just talked about, it means, okay, prove that the velocity is always positive. That's what it's really asking us to do. Well, if we need to prove the velocity is always positive, we certainly probably need to find the velocity function. So let's actually take the derivative of the position function s of t. That will give us our velocity function. So if I take the derivative of s of t, that would give me 1 over 1 plus t squared. Of course, you all remember the derivative of inverse tangent. Okay. Now it says prove that the particle is always moving to the right. Well, if you look at that function, is there any way we can plug in a value for t, okay, when t is greater than 0 and have that function be negative? No, you're squaring t and then you're adding 1 to it, right? So there's no way you can make velocity negative. So here's how I would maybe write it in one simple sentence. Again, we want to be very specific. So for t values, okay, where t is greater than or equal to 0, okay, v of t must always be positive, okay, which means the velocity is positive and the particle is always moving to the right. Okay, we try to be very succinct with this, but we need to be very specific too. So notice the things I said, right? I outlined where this is possible, or where this is true. T value is greater than or equal to 0. I used notation, v of t, and then I kind of explained what that meant. All right, a v of t is always positive. What does that mean about the particle? Don't assume the reader knows. Okay, you should make that statement. Okay. Prove the particle is always decelerating. Decelerating means the acceleration is negative. Accelerating means positive. Deceleration means negative. So if we're trying to prove something about the acceleration or the deceleration, we need to take the second derivative. Okay. So if we take the second derivative, we need to do a little quotient rule here. So low d high minus high d low over low squared. That gives me 1 plus t squared times 0 minus 1 times the derivative of the denominator, that's 2t, over the low squared, which is 1 plus t squared squared, which if we simplify it, it just comes out to negative 2t over 1 plus t squared squared. Okay, so if you look at that, again, first thing I would do is just looking at it saying, all right, if t is always positive or greater than or equal to 0, what do we know about the numerator? It's always got to be negative. Okay, so again, I may encourage you to pause it, the video, see if you can write me a succinct sentence here, outlining why it's always negative. All right, so here's what I would say. I would say for t values where t is greater than or equal to 0, okay, a of t is always negative, which means the particle is decelerating. How do I spell that? Decelerating. Perfect, okay. If we look at the next example, it talks about another position of a particle. It gives us the function. This time it's saying where t is in seconds, s is in meters. Find the velocity. What is the velocity? I'm reading through A through E here. When is the particle at rest? When is the particle moving forward? Okay. And all that stuff. I want you to kind of work your way through those, okay? And then when you get to E, okay, where it says find the total distance traveled by the particle during the first 5 seconds, okay? What it's going to require for you for this, okay, where it says find the total distance traveled by the particle during the first 5 seconds, is you need to find out every place where it stops. Okay, every place where it stops, and figure out the distance traveled in between each of those intervals. So let's say we start at time 0, and then it stops at 1 second, then it stops again at 2 seconds, and then it doesn't stop again to 5 seconds. Okay, what you need to be able to do is figure out how far it traveled between 0 and 1 second, how far it traveled between 1 and 2 seconds, and how far it traveled between 2 and 5 seconds, keeping in mind that it still may be in the same position. So we think about this in a particle that starts here, okay? Let's call that 4 and 0, a particle, okay, that ends back right up where it started. This particle traveled 8, what are we doing, meters? This particle traveled 8 meters. It traveled 4 meters to the right and then 4 meters back to the left. So that's why you need to figure out where it stops and calculate how far it traveled in between those times. So the key is, when is the particle at rest at part C? That is going to be an important part in part E, because you can see when the particle stops at 4 and goes back the other direction. That tells you when you kind of need to break it down and count those individual intervals. It's a little bit tricky. Give it your best shot. We can try talking about it tomorrow. But for the rest of class and for homework, try example 2. Talk about it with people in class. Use the solutions online. Try example 2. Okay. And notice it goes on to the next page. Some of them will be hard. Okay. G might be tricky. When is the particle speeding up? When is it slowing down? Okay, take a minute to think about those, do your best, and then we'll talk about it tomorrow.